Welcome back to another video. My name is Jesse. I am a tutor in Melbourne and I also make GAMSAT videos as well. This is set number 15 of the sample section 3 walkthrough videos. These have been really heavily requested in my feedback form. If you haven't already done my feedback form, I've linked it below. I'm collecting a whole bunch of data on people's performance and how this channel actually helped them in preparing for the March sitting, and hopefully using that to then adjust the way that I create content going forwards into the September sitting and into the future as well. As well as that, it'll also help us kind of understand a little bit more about what really goes into high performing scores of different students. Anyway, enough of that. Let's just dive right into it. Basically, if you're looking for the questions, you can find them all on my resources page. It's linked below. You can go down to the middle, although I'm hoping to clean up the page pretty soon and organize a little bit more as it gets busier. And you'll find around about the middle there's a table with a whole bunch of section 3 questions, and you can go to set 15. You'll find these questions. You'll also find this video embedded in there. So this effectively acts as a walkthrough and worked solutions to it. So if you want to pause the video as we go through, or if you want to do them in your own time and then come back and watch this, you can then see if your reasoning was correct. Keep in mind that what I go through might be one way to do it. There might be other ways that I'm actually not familiar with as well. All these questions I write myself. They're not stolen from anywhere or anything like that. So if Ace is watching, no, I do not leak any of your questions or anything like that I've seen. I try to, as much as possible, write questions that I think are truly reflective of the style of skills that get assessed. We know that the material from ACER is somewhat outdated now. It's probably still the best resource we have, but the test always evolves. And so I would hope that I am making content and making questions that are actually really useful and helping people really practice the skills that we're seeing in the test as well. Anyway, let's dive right into it. So the first one that we've got is technically a bit of like organic / physical chemistry, but we're not going to be using a huge amount of chemistry knowledge in it, as we always say. And then the other one after that is some physics as well, which looks very technical. And yes, it is presenting a theoretical concept, but it actually becomes a platform for your maths as well. So we'll dive into that. All right, so first of all, we've got this one here. So metal ions can be surrounded by and attached to solvent molecules or simple ions called ligands to form complex ions or coordination complexes through a process called chelation. The central metal ion M is usually a transition metal, and the number of ligands L and its coordination number N is equal to the number of attachments to ligands on the metal ion. Now that's a huge amount right there. So how would we make notes on this? We could use the stem, or what I would probably do is try to draw it out. Go, okay, so metal M, and it's attached to ligands. I'm just going to put like a bunch on there. I might just put 2 to keep it simple, to make sense of it, like this. And then it says its coordination number is equal to the number of attachments. That's N. So I'm just going to write N equals 2, and then is equal to the number of attachments to ligands on the metal ion. There we go. That's everything we need. So I've written it in general terms, right? And I've done an example to try and help facilitate my understanding of it, rather than trying to rewrite the words that they've already given me, or that I've given myself, I guess. I say they. I often, when I'm writing this, I speak as if someone else wrote the question. Yes, I did write them, so I do already know the kind of mechanics behind it, so to speak. But I try to give the feedback as if I were to be writing this, to be answering this question blind almost. So first of all, we've got ligands can vary in their attachment structure and can be classed as monodentate, bidentate, and tridentate, etc. We've got some examples. So monodentate, bidentate. We go, okay, what's changing here? So it's not the number of ligands, it's more so the number of attachments that it makes to the metal. So mono, bi, and tris has got 3 attachments to it. There we go. It technically does come down to like some Latin. They would refer to it as like biting onto it almost. So it's like 2 teeth kind of thing for bidentate, and tridentate, 3 teeth biting onto the metal. The stability of the coordination complex refers to the relative proportion of each species in the equilibrium state, and it's measured by a stability constant beta, which is given by, and it's just the product of a bunch of equilibrium constants all the way up until the last one, where K is the equilibrium constant for each chelation of a ligand in a coordination complex containing X ligands. Now that is technically a lot to take on and might be a little bit confusing. So sometimes what you'll see is that the information will kind of feed together as you go. So just keep pushing, basically, keep pushing through the stem. So for example, and here we go, we've got an example demonstrating how this works. A coordination compound with 3 attached monodentate ligands can be formed according to the following equation. 3 of them, they attach on, they make Ml3. That makes sense. We can see where this is the overall product of 3 individual chelation reactions given by. So we can do it step by step. We add the first one to make Ml, and it has its K value. Then we have Ml plus another one, makes Ml2, we have another one, and then finally it forms its final phase, Ml3, and there's the other one, like that. And so these are the individual K values that multiply to give our beta value. So it says, what are the dimensions of beta for a coordination complex with a coordination number of 6 and only bidentate ligands attached? So first of all, if it has 6 attachments, but each of those ligands takes up 2, then it means 6 divided by 2, it has 3 ligands. So what that means is it has 3 levels, just like this one did, although this was a monodentate. And so that means that the beta value would be K1 times K2 times K3. If we think about what the units are, dimensions you can do through units or just through dimensional analysis. Let's go through units, right? So I'm going to free up a bit of space here, actually, now that we know it's got 3 ligands. So the first one, I'm just going to follow this basically. So I can see that it would be moles per liter divided by moles per liter times moles per liter, not to be confused with the metal ion. So that would give me per moles, like that. There we go. So would this one. This would be moles times by moles times moles, which is per mole every time. So therefore there's the units of K1, K2, K3. So it would mean the units of beta would just be multiplying them through that formula. And therefore we get m to the negative 3. So then the next thing is, watch out, because dimensions, capital M means mass, not moles per liter. Moles per liter is a unit. So next up, I should have probably put an answer that said m to the negative 3 just to mess with people. And from there we go, right, what is moles per liter? It's concentration, which is number of moles per volume. So concentration is moles per volume. I keep writing the wrong thing. And I go, wait, number of moles is not a dimension. What is number of moles? That is mass over molar mass. Volume, but molar mass doesn't really have a dimension to it. So instead, we're just going to get its mass, that just kind of cancels out in terms of its units, per volume. And volume as a dimension is length cubed. So there we go. So now we know that if we're putting that to the power of negative 3, because that's the units, we go, all right, what are the dimensions of m to the negative 3? So that would be m to the negative 3, mass to the negative 3, and then L to the negative 9. Now I've flipped that just because I'm running out of space here. That would be ML to the negative 3 to the negative 3, and I'm raising that power to each of them like that, and therefore I get, this is my final answer. And so from that, sorry, that should be a positive 9. What am I doing? Where are we? Positive 9. And the answer is going to be B. Ignore the little typo there. I will have already fixed it. I just make lots and lots of typos. There we go. So the answer should be B if you got that one. Question 2. So then the following information also relates to question 3. That's just me being lazy. I didn't really know how to fix that. I realized that the next question had to use this info. So just keep that in mind. You might use some of the knowledge from this. If a coordination complex has a coordination number of 8, and so therefore n equals 8, and then it says, and it contains m bidentate ligands and n tridentate, and we realize, damn it, I've reused the letter n, so that's a bit annoying, so we'll get rid of that. And p monodentate ligands, what value can p not take? So this sounds like a chemistry question, but it ultimately is just going to be like discrete maths and probability almost with a sample space. So how are we going to do this? We have 8 attachments to make, but the bidentate ones take up 2 each, and the tridentates take up 3 each. So the number of attachments, let's do it that way. Number of attachments has to add up to 8. So it's going to be 2 for every m, plus 3 for every n, and then plus any monodentate 1 per those, and it should add up to 8. And there we go. So now we have to think, all right, what values could p possibly take if m and n are both variables? So we don't have simultaneous equations to be able to solve this. We have to go through the options. So let's start with m equals 0. And we go, all right, well, that means that n, what could that be? So n could be 0 as well. That's one case. We could also have n is 1, and we have to start thinking how many places do we have. So remember that n is 3 places. So really you could have no bidentates, and therefore you could have 1 tridentate. That would make up 3 places of the 8, but you've got none of them, so you'd have none. You'd have 1 tridentate, and that would mean you'd take up 3 of the 8 places, but you could also have a second one and take up 6 of the 8 places, but you could not have a third, because that would take up 9 places, which we don't have. So these are our different options here. I'm going to come back to getting P in each case. Then I'm going to logically go to the next one. What about when m equals 1? Again, we could have no tridentates. Now remember, if you've got 1 bidentate, then it means that there's only 6 places left. So you could have 1 tridentate, or you could have 2 taking up all 6 remaining places. So again, there are 3 different cases here. Then we go up again. What about when m equals 2? We could have no tridentate again. We could also have 1. So that would mean now, if we think about it, there's 2 bidentates, that takes up 4 places. We've got a tridentate taking up another 3. We don't have space for another one, so that's as far as it can go. What about if we have 3 bidentates? That takes up 6 places. We now do not have an ability to have any tridentates. There's only 2 places left. And then finally, m equals 4. That could take up all 8 places. And again, obviously no place for those. Now let's go through how many monodentates need to make up the remaining places. So here we had none, so all 8 it could be. Here we have 1 tridentate, leaving 5 places needing to be made up. Here we have 2 tridentates, so there's only 2 places left. Here there's only 6 places left because 2 of them are taken up by the monodentate. So if there's no tridentates, 6 need to be made up. If 3 of them are taken up by the tridentate, there's 3 left over. If all of them are taken up, 0 monodentate available. If we have 4 places taken up by 2 bidentates, I know this is sounding all very similar, hopefully following along, then it means there's 4 places left for monodentate. If we take up 3 of those 4 places with a tridentate, there's only 1 left. And then if we have 6 places taken up and no tridentates, then it means we have 2 more to go with monodentate. And then if all of them are taken up by bidentate, then we have no places available for monodentate. So which of these numbers did not feature in our sample space? And it was 7 did not appear. That's the one that P cannot take on every single combo. So that is like a time-wasting question that is reasonable to ask, but to do it in 2 minutes, you have to really logically break down how you're going to set it out. So there you can see I've gone case by case and I've used marginal changes one by one and considered all the options before moving on each time. And once I get into the pattern, it makes it easier for me to apply so I can kind of speed up as I go. All right, let's move along now. So then that was a pretty heavy question. The next one, which of the following expressions correctly calculates P in a complex with coordination number W? So we can kind of use our learning from the previous one. If there are W places to take up, then what you would have is there'd be a number taken up by the bidentates. So that'd be 2m, 2 for every one of them. But then you'd also take up 3 for every tridentate. And the leftovers is what P was. But we only really learn that by analyzing the first question. So make sure you do them sequentially. So there we go. We get answer C, nice and quick, we solve it. So then which of the following correctly calculates the equilibrium concentration of ml2 from the above general example? So if you remember, we had ml2, that was formed, let's just actually grab it from here. From this, let's actually screen grab this straight in. Let's put it here so we don't have to scroll too much. Okay. And we have to just come up with a new expression for it, basically. So if we look at the options, it seems to be linking more to M and L from the options and ML, so it's kind of pointing us up this way. So all right, well, let's start with K2, right, because that's got ML2 in it. K2 was equal to ML2 over, and I'm going to ditch the square brackets for now just because it's a bit tedious to write. I'm just going to make sure I separate them. I'm going to, okay, best case scenario is I just solve this equation for ML2, and that would be K2 times ML times L, and that should get ML2. And then I look to the answers and I can see, nope, it's not there, damn it. So I go, all right, or we've got to find something else. So if I look at them, which one has bits and pieces of my answer? K2, ML, and L. I can see, there's K2, there's L. It's squared, but there's L. That's the only one that's looking pretty good, so I'm going to try and investigate if that one's true. The bit that is not in the answer is ML. So I go, all right, let's try to find a way to find an expression for that. So I'm going to go up because all the information was hinting up to this data. K1 was ML over M times L. Now I'm trying to solve for ML to get rid of it. So K1 times M times L should equal ML. So now if I do that, I can replace this in here and I can get K2 times K1 times M times L and then times the L that I had over here. And that is going to make L squared. So it's K1, K2 for neatness, M, and then L squared. And there we go, that's the same thing, and that matches. And if it didn't work, I would just keep testing that theory and keep going through the other options. The next one I've scribbled all over, so let's get rid of some of this. Assuming that K1 is greater than K2, which is greater than the next, and so on, all the way down to Kx, then beta will be what? Now, again, this is actually, you can see the stem has turned into much more of a math stem than anything else. So remember that beta is the product of all of those, all the way down to Kx. So I would test the theory on each of these. So is beta going to be less than K1 when Kx is greater than 1? So Kx is the smallest of all of them because K1 is greater than K2, which is greater than, and so on. So it implies Kx is the smallest one. So that means that if Kx is less than 1, K1 could still be greater than 1. It could be 2, it could be 5, it could be 10 million, right? Any number. So when I multiply numbers that are greater than 1, what do I get? I get a number that is bigger than the number that I started with. So for beta to be less than K1 is very unlikely, because if it was like 5 is greater than 4 is greater than, and then Kx was just, let's make that the third one, let's say it was like 0.5, then I could have 5 times 4 times 0.5, and then that would give me 10. And 10 is clearly not less than K1, it's greater than K1, because K1 was 5. So I've already proven, I like to test with numbers whenever I'm not sure about the mathematical statements, just plug in some numbers that agree, see if it holds true. Is it less than K1 for K1 is less than 0? So K1 less than 0, that would mean that it's negative. So if you've got negative numbers in there, and K1 is greater, so say K1 is like -1, if that's greater than K2, then K2 has to be negative as well. Now when you multiply negative numbers, it flips between positive and negative. So you might start to overthink that and be like, well, it kind of depends on what X is, how many there are. The other thing is though, keep in mind, it's almost a trick answer. K can't be negative, because think about what K is. It's hinted at in the stem. K is just a ratio of concentrations. Concentrations can't be negative, so you'll never get a negative ratio. So that one is just false altogether. Then we have less than K1 for K1 is less than 1. Almost the same as A, but this time it's K1. If K1 is less than 1, and we know that K is greater than 0 all the time, now we know that if we had something like 0.9, the next one has to be less than that, maybe 0.8, which is less than, maybe 0.7. When you multiply fractions of 1, they get smaller as a product, right? They get smaller than the first one. So this is going to shrink the number down further and further. And so that would mean your answer, beta, would be less than the initial starting value. So that is looking pretty correct. And finally, is it going to be equal to K1 for K1 is equal to 1? If K1 is equal to 1, but K2 is less than it, even just on that alone, it's immediately when you multiply them, it's not going to give you 1 again. So it's already failed on the first one. So therefore D is out. There we go. So hopefully that wasn't too fast in terms of the mathematical reasoning. You can see that with inequalities, I like to just kind of choose numbers that satisfy that inequality and test the theory. And if it works, I try to test it until it fails or until I'm satisfied that it's pretty consistent. All right, cool. So now we get into a heavier kind of physics stem. Although I say heavier, it's mostly on maths rather than actual knowledge of physics. So we've got Einstein's theory of special relativity. You do not need to know special relativity for the exam, at least not from what I've seen. So just follow with the stem instead. So I've written here, it describes the distortion of time and length when observed from differing frames of reference called inertial reference frames, with a large velocity difference v close to the speed of light c. The theory explains the apparent dilation of slowing of time when measured on a moving clock relative to the observer and the contraction of apparent length. Actual time, t0, is that which is measured on the device in the same inertial reference frame. You can see it's linking all the words now, as the observer, and dilated time is measured on the device in the moving inertial reference frame to the observer. So basically what that means is, if I am like on a skateboard going down a hill and I look at my watch is not moving relative to me. It's in the same reference frame as me, despite me moving. So therefore time will not appear to dilate. However, if I was to look at a clock on a wall as I whizzed past, then because I'm moving and there's a speed difference between me and the clock, then I would see a dilation of time. Realistically, I'd have to be going at close to the speed of light to be able to do that on a skateboard. Slow, kind of everyday speeds, you're not going to see any relativistic effects. You need to be at a very high fraction of the speed of light to be able to do this. But that's the concept of actual time versus dilated time. And the same thing, length. If I try to measure length, like if I try to get a ruler and I try to measure the length of my forearm or something like that, or the length of my leg or something, then it's going to be the same as it normally would be because my ruler or my measuring tape is not moving relative to me. If someone else tried to use a ruler to measure something that was moving, or they tried to measure something on a moving ruler, then it's going to look like it's contracted in length. Then it says, likewise, actual length L0 and contracted length L are described in the same way. We've got some formulas here with this gamma symbol, which is the Lorentz factor given by this. So you can see I've segmented the formulas rather than putting it all together. And then because this is a distortion of perception, this phenomenon only applies to observations of velocity that is perpendicular to the observer's viewing direction. So what that really means is that if something is moving towards you or away from you, you won't notice any relativistic effects. If it's moving past you perpendicular to your line of sight, then that means that you will see relativistic effects. At what approximate percentage of the speed of light would an object need to be traveling to appear to be half of its actual length? So we're talking about lengths, so it links us to the formula. We go L equals L0 over gamma. Then we go, all right, so L has to be half of L0. We plug that in, and then we go, all right, what does that do? So we can switch these out. We can put the gamma over here, and we can put the half underneath here. Half L0. The L0s cancel, and we end up with gamma equals 1 on a half, which is then going to be 2. So then we go, right, so how do we make gamma 2? Because we've got to go to velocity. So gamma was 1 on the square root of 1 minus v on c all squared, where v was the velocity differential and c is the speed of light. So we put 2 in, and we have to solve for the velocity, v on c all squared. And now it's just a maths question. So we're going to go, we're going to switch these out again. 1 minus v on c all squared is equal to 1 on 2. We can square to the other side. V on c all squared is 1/4. We square both the 1 and the 2. Then we can minus the 1. We get negative of v on c all squared is equal to negative 3/4. The negative cancels. We then square root, and we get the square root of 3 on the square root of 4, which is 2. And this is actually the fraction of the speed of light here. So we can kind of stop here for a moment. Now, I always say that knowing the square root of 2 is 1.4 and knowing the square root of 3 is 1.7 is a really handy tool. I don't think they would ever write questions like I have here, I guess, that 100% rely on it. They'd probably give you the note, but I find it's really good as a good shortcut to work through maths questions and find shortcuts in the estimation. So this would be 1.7 over 2. Now, if I want that as a decimal, that's a bit hard to do. So I might try to actually halve it, or you could go, it's 17 over 20 by multiplying them both by 10, and then knowing that a 20th is 0.05. So there's 3 20ths off, so that's 0.15 off of a whole. So it's 0.85 or 85% of the speed of light. You can also prove it, because if v on c is 0.85, v, you times the c up and get 0.85 c. 85% of c, 85% of the speed of light. Cool. The next one then, so a graph question. We've got which of the following graphs correctly describes the change in time and length with increasing velocity? So this we have to kind of qualitatively and graphically kind of analyze the formula. So if we look at the relationship between them, we know that time increases with increasing velocity, and then we also know that length decreases. So this already helps us quite a bit. It means that the ones where time is going up should be useful. So this is good, this is good, this is good. Whereas this one down, so B, that's wrong. That should be C, and that should be D. These already, D is already going to be out just on that alone. You can also see that length is going up when it should be going down. The next thing then is, what kind of relationship is it? Is it linear like A suggests, or is it non-linear like B and C suggest? So if we look at these, the time dilation, we can see that there's a non-linear relationship in the formula because it links to gamma, and gamma has a non-linear component to it. So if we break that down, we can actually see that it'd be 1 on, let's substitute it in, 1 minus, and it's v squared on c squared, like that. And then from there times t naught. So t is proportional to the inverse of the square root of 1 minus v squared on c squared, like that. Oh, didn't get the squared on that one. So if we track that through, if we were to increase the velocity here, then what we do is we push this fraction closer to 1, right? We're getting closer and closer to the speed of light. Which means that this here, when we minus something that is approaching 1, then we're approaching 0 in that case. So then we're square rooting something that is approaching 0, and then that will be a very small number, so that will be still pushing it down. And if you decrease the denominator, then you increase the overall fraction, and it's exponential because of the square root relationship. And that is why now we know it's an exponential growth. And so it's going to be either B or C because they both show that. The difference between these is how length decays. So really you could already know that when you have an opposite, exponential decay always looks like this shape. The other way to prove it is this one looks to be becoming asymptotic or approaching 0 but never reaching it. This one is crashing into 0 as a length. So if you think about it, what happens when the velocity gets higher and higher? You get more and more relativistic effect, but this here approaches 0, right? And so then this whole thing approached 0. And then when we look at the formula, we can look at this over here. That would mean that as the denominator approaches 0, 1 over something getting closer and closer to 0 is actually getting infinitely large. So that is approaching infinity. So then if gamma as a whole is approaching infinity, what happens when you divide a number by infinity? It approaches 0 again, and it approaches, not crashes into it. So therefore, it'll be that one there, and so answer C is our best bet. And then finally, we have questions 3 and 4. So question 3, if an astronaut on the surface of the moon sees a comet hurtling directly towards them at a speed of 99% of the speed of light, what proportion of its actual width would it appear to be according to the astronaut? Now, this one is basically, I'll give it away, it's a trick question. It's actually just D, because the comet is coming directly towards them, which means that there is no perpendicular velocity or motion, so therefore there's no relativistic effects, even though it is moving very, very quickly. So realistically, it's going that fast that the light coming towards it, these are always really interesting. You got the moon, you got someone standing there, and then you've got a comet just like hurtling towards them. It's already coming at the speed of light, at 99% of the speed of light, and then the light ejecting off of it so that they can see it is coming at the speed of light. So technically the light reaching them is coming at 1.99 times the speed of light. The idea is that it's not moving perpendicular to them, so there's no relativistic effect. It wouldn't warp in any way. It would have to be moving across their field of view for them to see any warping. So therefore there's no length contraction. And then question 4, which of the following observations would produce the greatest contraction in absolute length measured in centimeters? So we've got all these different objects of different lengths traveling at different velocities, and notice they're all in non-standard units, kilometers per hour. There's a good trick, if ever you need to convert kilometers per hour into meters per second, you basically just divide it by 3.6. The reason for that is because you turn kilometers into meters by multiplying by 1,000. You turn hours into seconds by multiplying by 3,600. And if you look at the ratio of these two here, there's a 3.6 ratio between them. That's the kind of shortcut connection, but we can see which of the following observations produce the greatest contraction in absolute length, not by proportion. So we don't care about the V over C ratio. We just care about which one would shorten by the most distance. So you can actually plug in all the numbers and convert all those, but you've got to then convert those into meters per second, which is going to take forever. The quicker way to look at it is just to say, all right, well, things that are moving faster have a greater relativistic effect. So we know all things held constant, higher velocity equals more length contraction. So we create little rules of I want high velocity, and then the other thing would be a longer object, right? Because it's all by proportion. So if it's a bigger object, 1% of a big object is greater contraction than 1% of a small object. So we actually want large actual length as well. So what are the largest actual lengths? So we've got 80 meters and we've got 16 meters. So these are much, much greater. So already I'd be pointing at these. Now the next thing would be is what are their velocities? This one's got 720. That's got the largest velocity. So velocity-wise, it wins. Length-wise, it also wins. And therefore my answer is C, and I don't have to do any maths on it whatsoever. So always keep in mind, you can create these simple kind of logic rules, and you can answer questions by avoiding the maths entirely. Often when you feel like the maths is going to be too tedious, it's probably because it is, and they're looking to see if you're going to reason with it instead. And that is following on from the information given in the STEM. Notice that yes, this is a concept from physics. You do not need to know anything about it. You don't need to come away from this going, I need to review special relativity. It's a math STEM more than anything. And it's about understanding what this formula is actually demonstrating for us. And it shows us that there's an inverse connection between these two. One of them multiplies by gamma, the other one divides by gamma. So they'll have opposite wants in terms of what will happen, or opposite outcomes, I should say, in terms of high velocities and so on. And then you can reason with the concept of velocity going up by plugging it in here and thinking about just an increasing number. If you don't like using the arrow method, you can also just actually test, like, what if I make V well, you'd have to use the speed of light. So what if you make V over C like 0.5, and then what happens if I make it 0.9 or 1 or something like that? And you can test the effect of increasing velocity that way if you're not too sure and not trusting it. But anyway, that's enough rambling for me. That's pretty much everything. Hopefully you got through these 9 questions pretty well again. It's another 9. So I think if I'm right, I think we're up to like 138 now on there. So hoping to at least hit 200 before the September sitting. They take a bit of time to write, but I'm going to try and bang as many of these out for you guys as possible. Otherwise, like the video if you liked it. I don't normally say this because I never really think to do it. I just leave the little Danny DeVito thing up. But I have noticed that the channel has kind of slowed down, which doesn't really bother me all that much, but I know that making sure that it reaches as many people as possible is pretty important. And so if you haven't already subscribed, go ahead and subscribe to it. It doesn't cost you anything. If anything, it just means that you don't miss any of the videos if they are useful. Then again, if you're looking to avoid me, then don't subscribe because you'll get a lot with the posting frequency that I have. Otherwise, that's pretty much it. If you haven't already subscribed, go ahead and do that. And if you haven't liked the video, like it. If you enjoyed it, down thumb it if you still can. I can't remember if YouTube still allows that, but if you didn't find it very helpful, go ahead and let me know in the comments and roast me there. But anyway, I'll leave you guys for the rest of your week, and I'll see you guys in the next video.